This is Introduction to VLSI Design class, and today we will talk about combinational circuit design, where we will apply our previous knowledge in the previous videos in simple combinational circuits. So we will talk about the bubble bushing, the compound gates. We will try to apply the logical effort in finding the delay of certain designs. And then we will talk about different aspects like input ordering, asymmetric gate, skewed gate, and so on. So as an example, this is a very low code for the multiplexer, where you have the input D0 and D1 and the selector line. This is a 2-to-1 mux, and a single output, which is Y. And you assign Y based on the selection. So if the selection is equal to 1, you get D1. If the selection is equal to 0, you get D0 and the Y. And this is how you write this module in Verilog. Now, if you were asked to sketch a design using AND, OR, and NOT gates, this is what you would do if you use symbol gates, the one that we studied in logic design. So you have D0 with S bar and D1 with S. You have two-level design. You have two input ANDs followed by an OR. So you can see that the output is going to be D0 when S is equal to 0, and it's going to be D1 when S is equal to 1. Now, if you were asked to sketch the design using NAND, NOR, and NOT gates, assuming that the S bar is available, so you don't have to put an inverter. So usually we have this assumption in every circuit that you should assume both signals and their complements are available. The reason is at the beginning, when you have the inputs, usually they are stored in the memory or the main memory or the cache. And the design of the memory, we'll talk about this in a later chapter. And every memory cell, it can give you the output. If you want to read the memory cell, it can give you the output and the output bar. And this is why we assume or make this assumption. Now, to convert the previous design to NAND and NOR, you simply add these bubbles where they can cancel each other without changing the functionality. But for adding these bubbles, now we convert this previous AND to NAND. Similarly, here we convert it to NAND. And now this is actually an input inverted or simply another NAND circuit. So to apply the idea of bubble bushing, you actually start with a network of AND and OR gates, and then you convert to NAND and NOR with the availability of the inverter by adding the bubbles. You also usually apply De Morgan law. To apply De Morgan law, remember that the NAND is actually an inverted input OR. Similarly, the NOR is actually an inverted input AND. And to do the simple application of De Morgan law, the NAND is actually, if this is A and B, it's A ANDed with B all bar. And this one, when you break the line and change the sign, it becomes A bar or B bar. And this is actually the exact same gate. You can do the same for the NOR. So, but if this circuit, this is what you have, you simply add the bubble and inverter, bubble and inverter. And for the OR, you can add the bubble and an inverter. After this, you can push this inverter over there and you make it like this. And you can cancel those two because they don't have any reason, since this is an AND and this is an AND and this is also an AND. You can actually jump directly from here to there, like what we've done in the previous slide. But if you want to do it step by step, you can do it this way. Now, for the third example, if you were asked to sketch a design using one compound gate and one NOT gate for the same problem, what will happen is you say that the whole thing here is the compound gate. Notice that we removed the lines over there to indicate that this is actually a compound gate that we can do using CMOS, or we can design using CMOS transistor level circuitry. And this is a simple inverter. Notice that this bubble here makes the function, if we say that the function over here is, let's say it's y1, and after the invariant becomes y, so y1 is actually going to equal d0 ANDed with S bar, or d1 ANDed with S all bar. So this bubble is actually this bar, and we get benefit of this bar when designing the circuit in the CMOS circuit. So let's do it, and we will actually give you a few examples, and we will end up with one of them being looking like this one. So if you have a unit inverter, this is the inverter, and this is the design of the inverter. We know the sizing is 1 to 2, and we get the logical effort for A. Now we are indicating that the logical effort for every input is 3/3, and the parasitic is 3/3. Remember, the logical effort, we look at the gate capacitance. This is for logical effort. And for the parasitic, we look at the output capacitance. So let's do it for the other one, where you have AB or C or bar. This is a logic circuit for it. And actually, this is a compound gate. And you do this by having AB in series. Now you have the whole bar here. That's good. So we take whatever below or under the bar, and we make it or design it in the pull-down network. So you have A and B in series and parallel with C, as you can see here. Now, in the pull-up, you do the duality. A and B were series, so they are parallel. C is parallel with the group, so now it's series with the group. Now to size, you take the longest path. So at this point, you have 2 transistors, so it's going to be 2 and 2 if you compare it to the inverter. And this is a single one, so it's going to be only 1. For the pull-up, you have 2 transistors to the VDD. This is the longest path. And from that, you would say that if I have only 1, it would going to be 2. Since I have 2, so it's going to be 4 and 4. And this is actually parallel with this one. Now, from that, you can get the logical effort for A, B, and C. And you can notice that the logical effort for A is the input capacitance, where it is 2 plus 4, 6/3. Similar for B, but for C, it's slightly different since the sizing is different for C. So it's going to be 5/3. If you want to find the logical effort for the whole circuit, you can average these 3 numbers. Now, for the parasitic, you look at from the output side, where this out is actually connected to 4, 2, and 1, which is going to be 7. And you compare it to the inverter, which is going to be 3, 7/3. Now, for this circuit, that will actually look like the multiplexer that we just explained, where for the multiplexer, we had D0, S bar, D1, and S. Now we have A, B, C, and D, but it's the similar thing, only we change the input names or the input literals. So now this is the compound gate. You have whatever under the bar. A and B, they are series. C and D, they are series. The 2 group together, they are parallel. Now in the duality, A and B were series, so they are parallel here. C and D also series, so they are parallel. And since the 2 group, they are parallel here, those 2 group actually are series in the pull-up network. So let's size. So the sizing is similar to this path. So it's 2, 2, and 2, and 2. For the up, the pull-up, again, is like this one. So because you have 2 only transistors or 2 PMOS to the VDD, so it's 4, 4, and 4, and also 4. This circuit, A, B, and C, and D, all of them have the same logical effort, which is 6/3. A, for example, 4/2, and so on. Now, for the parasitic, again, now you can notice that this is not a common circuit where you can count the number of inputs and you say, okay, the parasitic is only 4. Sometimes you get this correct, sometimes not. So let's, for example, look at this one. This one, you have 3 inputs. You can't say that the parasitic is 3. We found it to be 7/3. Now for this one, there are 4 inputs, and let's check from the output side. The output is connected to 4, 4, 2, and 2. Add them together, they are 12/3. So luckily, we found that the result is actually all like what we were thinking that it is 4. For this circuit, you have 5 inputs, A, B, C, and D, and E. You have a bar over all of them. So you take whatever under the bar and you design it here. You have the B and C parallel, series with the A. And you have D and E, they are in series. Now those two groups, they are in parallel, as you can see here. Now whatever was parallel is series in the pull-up network and vice versa. So these were series, they are going to be parallel. Those or the B and C, they were parallel, so they are series. And they were series with the A, now they are parallel with the A. Now this group with this group, they were parallel. Now they are, the two group, they are in series. Now to do the sizing, this sizing in the pull-down network is similar to the sizing here and there. So it's very clear. For the pull-up, you would choose the longest path here. So the longest path, since you have 3 transistors, going to be 6, 6, and 6. If it is only 2, you would have 4 and 4. So you have 3, so it's 6, 6, and 6. This is parallel with this one, so it gets the same sizing. Now this one is in parallel with only these 2. How to find its sizing? It's clearly actually that it is halved. So if there are 6, it's only 3 here. But to give you a mathematical way to do this, just count the number of transistors here and say that there are 2, for example. The number of transistors here is 1. Now, you know the sizing here are 6, and you want to find the sizing here. Let's call it x. So what's the value of x? It's 6 times 1 divided by 2, which is going to be 3. If you apply this rule, no matter what circuit you have, you'll get the correct sizing. So now looking at the logical effort is actually for the A, it's 2 and 3, so it's 5/3. For the other inputs, like B, you have 2 and 6, so it's 8/3. And you can check it for the other inputs, they were going to be the same. Now for the parasitic, you can't say that they are 5. Let's look here, and you say that 6 plus 6 plus 2 plus 2, that's 16/3. That's 16/3. And that this is not equal to 5. So if you have for the parasitic, if you have a common circuit, you just count the number of inputs. If not, draw the circuit, do the proper sizing, and then look at the output node. Look at the output capacitance from the output node, count where it's connected, calculate the sizes, divide it by 3 to get the parasitic. So as you can see, up to this point, we are actually revising what we learned in the previous videos. So now let's see that you have 2 designs. And that's actually one of the outcomes that we want you to learn in this class. So you have 2 designs. In our case, it's just a multiplexer. So these 2 designs, you gave it, for example, to 2 different teams. The first team came up with this design, the other team came up with this design, and you were the engineer responsible for them, and you want to decide which one is better. So in terms of delay, you can do it using the concept of logical effort. So in this example, the multiplexer has a maximum input capacitance of 16 units. You could say 16 lambda, 16 units, and so on. It's actually giving you what input capacitance that you should expect at the input side. Also, it must drive a load of 160 units. This is what you expect in the output for both design, for this design and similarly for this design. So you expect the same. So it's 16 units of each design, and it must be having driving a load of 160 units. You were asked to estimate the delay of the two designs. So what should you have actually many ways to do it. You can do it mathematically using Shockley model. You can, because all of these gates are composed of transistors. So you go to the transistor levels, and from the transistor level, you go up to the logic level. You can do it using simulations like SPICE or SPICE or LT SPICE, these kind of tools. You can use the RC model or the RC ladder or the Elmore model that we discussed. Or you can use the logical effort. The logical effort is the easiest or the like the shortest way to get a reasonable results where you can compare those designs. So from these designs, you can see in this design, you have two stages. All of them are NAND circuits. You know the logical effort. You want to find the G, H, and B, and then the F capital, the F hat, the parasitic, and then you find the delay, which is the normal way that we described before of finding the delay using the logical effort. So for this one, two stages. The logical effort here is 4/3. The logical effort here is 4/3. This is for two input NAND circuits. You can multiply them together to get 16/9. The H, which is going to be the same for this circuit and this circuit, since I gave you what to expect at the input and the output. So it's 160 divided by 16. And notice, no matter what units I give to you, they will be taken out because you will divide them by each other, or you are getting actually the ratio. So 160 divided by 16 is 10 in both designs. Now for the branching, there is no branching here. Also in the other design, there is no branching, so the branching is equal to 1. This is the initial values that you should get. So let's move to the next design. Again, two stages. This is the first stage. This is the second stage. Notice that this is a compound circuit. So now we have two stages. The logical effort for this one is 6/3. How do we know it? Because we actually had this design before here. So what you're supposed to do, if you didn't do that before, is draw the circuit, size it, and from the sizing, get the input capacitance and divide it by 3 to compare it to the inverter. And you can find that it is actually 6/3 for every single input. So to get it for the whole gate, you can average these numbers, which is going to give you the same result, which is 6/3. So you have the 6/3 here, and here you have 1, the logical effort of the simple inverter, so it's going to be 1. From this, you get capital G is equal to 2 for the whole path. For the H, we said that it's the same also for the branching. Now it's simple mathematical calculation. So you'll multiply these three together, you get F capital 160/9. You multiply these three together and you get 20. And then you get the F hat, which is something that is very important to get the delay and also to get the gate sizes if you were asked about the gate sizes. So the F hat is actually going to be the square root, since you have only two stages, the square root of capital F, which is going to be 4.2 in this design, and it's going to be 4.5 for this design, since F capital is different in both designs. Now the parasitic, this is a common gate, 2 and 2. So 2 plus 2, and notice that we are adding here. You are used to multiplying in the previous calculation. Here you are adding. 2 plus 2 is equal to 4. Here is actually, this one is going to be, the parasitic is going to be equal to 4, as we explained here. So it's 12/3, which is equal to 4. So the parasitic is equal to 4, and for the inverter is only 1, so it's equal to 5, the total. Now you just say that it's N times F hat plus P in both circuits. This is N, this is F hat, and this is P. Similarly here, and this is also P. And you get here 12.4 tau, here 14 tau. So in terms of speed, in terms of delay. This design is better than this design. Now, if you were asked about the transistor sizes, about this transistor size, what you do, you should first look at the nodes that you want to calculate. This one, it was given to you that there are 160 units here. And this one, we're giving to you at the input, it's 16 units. You want to get what is the value that you should expect here at this point. So you go from the back, from the output side, and then you calculate it backward. It's only one calculation to find this node, similarly to find this node. And this is what we are going to do. So basically, we know our F hat in this design and F hat in this design, because we will divide by that. So it's 4.2, and we have 4.5. This is 4.2, and here 4.5. So what to do is going back from here, the 160, the capacitance at the output, you divide or you multiply by the logical effort of the NAND, which is 4/3, and then you divide by 4.2, which is the F hat, and you get 50. This is what we need. We know now that you have 50 here, and you have 50 here. Same idea. Now for this one, you know that you have 160. This is an inverter, so at this node, the logical effort of the inverter is 1, and divided by 4.5, you get 36. So at this node, you know that you have 36. Now, what you do, you're supposed to do the sizing, the normal sizing, which is going to be 2, 2, 2, and 2. Similarly for each one of those. This is the sizing of the 2 input NAND. For this one, the sizing, we already did it in the previous talk. So it's 2, 2, 2, 2, 4, 4, 4, 4. So it's 2, 2, 2, and 2, 4, 4, 4, and 4. And the last one is 2 to 1. That's the simple inversion. What you do is that you distribute the 50 to both of them. And we know it's 50% in the NMOS, 50% in the PMOS, since it's 2 and 2. And to do this, we explained in the previous video. I don't want to go through this again. So what happens is you have 50, so you multiply the 50 by 2/4 for the PMOS, and for the NMOS, you multiply the 50 by 2/4, and you get the 25 and 25. So you have 25, 25, 25, 25 here. Similarly, you know that the input is 16. So you make it 8, 8, and 8, and 8, and so on. Now for this side here, now you have the total is 6. Let me do it there. So you have the PMOS and the NMOS. So the total is 6. So you divide by 6, and you say that you have 4/6. And here you have 2/6. And you multiply it by whatever input capacitance that you have, which is the 60. And from this, you will get 6, you will get 10 in the PMOS, and you get 6 in the NMOS. And from that, you can plug in in the NMOS 6, 6, 6, and 6, and for the PMOS, you have 10. Now, for this node, we calculated 36, and you would say, okay, for the PMOS, we know that the inverter, you have 2/3 in the PMOS and 1/3 in the NMOS. So the 36, you multiply it by 2/3 to get 24, you multiply it by 30 and you get 12. And this way you did the size. So up to this point, up to this slide, what we did is actually a revision about what we discussed before. And you can see that we had 2 designs, and we chose this design in terms of delay. Now let's continue to kind of a new subjects related more to VLSI, like the input order. If you have, for example, a two-input NAND, should you say A and this node is A and this node is V, or you do the commutative property and you say, no, this one is B and this one is A. Since this is a NAND, if you say A NAND B or B NAND A, in functionality-wise, it doesn't make a difference. It doesn't make a difference. But now you have good knowledge to make certain distinction. So let's see. If you know that A arrived latest in this design, in the NAND, what will happen is the capacitance will be affected. So let's calculate the capacitance at the load, which is going to be 2, 2, and 2, which is 6C. And at this node, since it is shared, so you say it's 2C. Now what happens is, if you know that A arrived the latest, so it's late. So suppose that you are swinging both A and B to on, B will be on way before way before A. So A will be the latest. This is the latest event. It was off and now it's switched to on. So what happens at this state, actually this one was on before this input line. And now since this is on, what will happen is this capacitance will be discharged. So you don't have to worry about it. You don't have to worry about it. And you just focus on the 6C. 2 discharges once this one is on. Now, if it's the other way around, if B arrived the latest, so A was on before B, what will happen is both capacitance won't be discharged because this link is actually closed. It's not connected to the ground. And because of this, you had to wait until Mr. A becomes on. And now you have a full path to the ground, but you need to worry about both capacitors, which is the 6C and also to the 2C to discharge. So if A arrives latest, which is this case, your model will be R times 6C. You only worry about the 6C, which is going to be 2 tau. But if B arrives the latest, your model will include both the 6C and the 2C, which is going to be 8C. And this is actually 2.33 tau. So from this discussion, what we would say is we will make this distinction. We will have what we call inner input and outer input. The inner input is close to the output. Why? And the output or the outer input is close to the rail. Whatever is the rail, the VDD or the ground. In our case, it's the ground. So the rule here is if the input arrival time is known, then connect the latest input to the inner terminal. So the slow goes here and the fast goes here. The slow goes here and the fast goes here to get this scenario. That's basically the inner and the outer input. So now if you were asked, does it matter to have A and NAND with B or B NAND with A? If you know the arrival time, then yes, they matter. So let's jump to the next subject, which is called the asymmetric gate. The asymmetric gates. The asymmetric gates favor one input over the other. One input over the other. So if you have two inputs, A, and for example, here we have reset, which is active low in our example, you favor one input over the other. Maybe A, maybe the reset. When you look at it, you would say, I know that the reset, I do it only once at the beginning. What matters to me is this input, which is the real input, the A that changes like based on the previous case. Let's say. So what happens, since I know that I should favor this input, I will use smaller transistor on A, but to compensate for this, I will make larger transistors for this one. We know that this is a NAND, and the correct sizing for the NAND, the one that we described before, is 2, 2, 2, and 2. But now, since I'm favoring A, what I'm gonna do is I will reduce the sizing of the A and increase the sizing of the other transistor. This is the idea about the asymmetric gates. So they're not symmetric anymore. The resistance are not symmetric in the pull up and the pull down, because we care about the inputs more than having the resistance the same. What happens now after you do this, if you calculate the logical effort for A, it's going to be 4/3 divided by 3. So it's going to be 4/3 divided by 3. That's the logical effort for A. Why are we doing this? We need to calculate the logical effort of A, the logical effort of the second input, which is the reset, and then we will see the logical effort of the whole circuit, and we want to conclude what's actually the effect of doing this, reducing the size of the transistor in the favored input and increases the size of the other input. That's what we want to do. So let's find the logical effort of A first. So for the A, we said that the sizing here is 4/3, and we didn't change the sizing in the PMOS. So it's actually going to be 4/3 plus 2/3. So it's the input capacitance divided by the inverter input capacitance that we compare to. So from this calculation, you know, the 2 is going to be, you need to calculate the addition here. So you would say that it's going to be 10 over, this is going to be 10/3 divided by 3. So at this point, this is what the logical effort of A. The logical effort for B, or for actually the second input, which is the reset, is going to be 2 plus 4, which is going to be 6/3. 6/3 is equal to 2. Now, if you remember the logical effort of the NAND, the logical effort of the NAND that we know, 2 input NAND, we said that the logical effort is 4/3. So let's compare the 4/3 for each one of them. You can see that for this one, it's 10/9. If we get the equivalent for this one, and you multiply by 3, and the numerator and the denominator, so it's going to be 12/9. So comparing 12/9 and 10/9, you know that the logical effort here and for GA is lower. You are getting GA actually to a better logical effort. But for the B, you are increasing this way more. It's now 2. So now if we want to get the total for the circuit, you can get the G total with adding those two. It's going to be 28 divided by 9. That's the total logical effort. You should actually divide this by 2, so to get the idea of what's going on. So if you divide this by 2, you get 9. I think 9. So you'll divide the 28 by 2. So you'll get it like this, and the 28 divided by 2 is 60. No, is it 14? So it's 14/9. I got the 14/9, and this 14/9, if you compare it to the result that we got, which is 12/9, still it's bigger. That's the whole idea. So yes, you are getting the logical effort for A that we are favoring lower, but for GB, you are increasing that. And for the whole thing, the total, you are actually also increasing. And this is what we get from the asymmetric gate. You approach the logical effort and make it almost 1 on the critical path. You can see here, it's almost 9/9, which is equal to 1. But the total logical effort goes up, as you can see. So that's the idea of the asymmetric gate. You can make them symmetric if you like. Again, this is for the NAND. We are talking about the NAND. You can make them symmetric by having this. How? Now, you can say that, especially for the inputs, should you do A and then B or B and then A? Which one to favor? So to make them symmetric, what you do is you will add 2 more transistors here. Like if you cross these, you'll end up with a simple NAND circuit. But if you add those 2, and then you make them one time, well, A is near the output, and the other time the A is near to the rail, and similarly, but in the opposite direction for B, you get the symmetric gate. Now, the thing about the whole asymmetry here, how much you're supposed to lower this transistor? How much you are supposed to increase this transistor? There is a lot of talk about this, and there is many ways to do it. But the most important one is actually the skewed gate. The skewed gate. You have similar idea, but now we are favoring one edge over the other, or one transition over the other, not an input. The transition itself we favor. So either we favor what the pull up or we favor the pull down. To explain this, suppose rising output of the inverter is the most critical. So we care about the rising. We care about the rising. So now we are caring about the edge. How to rise? You should make the pull-up network on. This is the way to rise the output. So what we will do to explain the skewed gate for you, first, we know this inverter. This inverter is called now the unskewed inverter, where you have the equal rise resistance. So you have the ratio 2:1, as we explained. If you divide this by 2, both of the pull-up network and the pull-down network for the inverter, you will get 1 and you will get a half. So this now is an unskewed inverter. Both of them are unskewed, but here we care about the critical input for us, which is the pull-up network. So you do this, and this is for equal rise resistance, and this is for equal fall resistance. Why we are doing this? Like this one and this one have the same ratio, but why we are dividing? The reason is, if we want a high skew inverter, what you do, you have the red circle and the blue circle. The red circle is the critical or the favored transition, which is the pull up now. The blue circle is the non-critical or the sacrifice transition, which is the blue circle. So what happens here is we will keep the sizing of the pull-up network to be like this one, which is the normal inverter. And we will sacrifice this one by half. So we are actually taking this half from the other halved transistor, let me say, halved inverter. So you have 2.5. And basically, you can get this idea directly without even getting these. So you know that you want this one. This is the one that you favor. This is the critical one for you. You keep the sizing as you know. The sizing is 2:1. That's what you know. So you keep the 2, and the other one you half it. So it was 1, it's going to be half. That's the whole idea. Now, to calculate the logical effort, you compare to the unskewed inverter with the same effective resistance. And this is why we have these. So for this one, you should compare it to this inverter. And for this one, you should compare it to this inverter. How to do this? You get now the transition logical effort. You have only one input. And since the beginning up to this point, we always get the logical effort for the input. Now we got the logical effort for every transition, for the up and for the down, or basically for every network, for the up and also for the down. Now, the input capacitance is 2.5. So it's 2.5 in both of them, whether you are up and down. The difference is the denominator. For the denominator, for the critical input, the one that you favored, you do the same that we know before. You divide by 3. You compare it to the normal inverter, so you divide by 3. For the one that you sacrifice, you divide by half that amount, which is 1.5. We get the 3 from adding those two. We get the 1.5 from adding these two. And that's the whole idea. To define it better, we would say that the logical effort of a skewed gate for a particular transition is the ratio of the input capacitance of that gate to the input capacitance of an unskewed inverter, delivering the same output current for the same transition. So for that example, for the up, we get this one. For the down, we get this one. Now, the skewed gate reduced the size of the non-critical transistors. So the non-critical, we sacrifice them. We say that they are not critical. For the high skew, we care about the up, so we sacrifice the inmost or make it small. For the low skew, we favor the actually fall or the pull down network. So we make the PMOS halved or smaller. So basically, the logical effort, what will happen to it, it's going to be smaller for the favored direction, but larger for the other direction. And we will calculate it for some of the gates, like for the inverter, for the NAND, if it's 2 input, and for the NOR, if it is 2 input. The unskewed is the one that we explained before. This is the inverter 2 to 1. The NAND is 2, 2, 2, 2, and the NOR is 4, 4, and 1, and 1. From this, you get the up and down. Now we care about the transition, the network, the pull up network and the pull down network, GU and G down. We get the logical effort for each one of them. So the GU is equal to 1. Why? Because you would say, let's do it this way. So just to explain it to you, for this one, it's actually unskewed. So you get the same result as the normal logical effort. So the logical effort here is 2 and 1. So it's going to be 3 over 3 is equal to 1. Similarly for the down, 3 over 3 is equal to 1. And the average is 1. And we said that the logical effort of the inverter is equal to 1. For the NAND, it's going to be 4 over 3 for each one. The NOR is going to be 5 over 3. Again, here is 2 and 2, so it's 4 over 3. Here is 4 and 1, so it's 5 over 3. Now for the high skew, if you care about this one, this transition, the up, then let's calculate it again here, GU and GD. GU and GD. GU, similarly here, and GD. So what you will do, since you are favoring the pull up network, you will divide by 3 in the pull up network. You are sacrificing the pull down, so you will divide by 1.5. That's basically the whole thing. Now, since you are sacrificing this, you will halve its sizing. You are sacrificing this one, so you'll halve its sizing. Similarly, you are sacrificing this one, you will halve its sizing. Now, for each input, or for this input, it's 2.5, so it's 2.5 in both of them. For this one, it's going to be 3. And here it's going to be 4.5. And from this, it's actually what's written here, but they get the equivalent fraction, which is 2.5 over 3 is actually, if you multiply by 2 and 2, it's going to be 5 over 6. 2.5 over 1.5 is going to be 5 over 3. And you can average them to get 5 over 4. The 3 over 3 is equal to 1. 3 over 1.5 is going to be equal to 2. This is clear. And the average is 3 over 2, or 1.5. And for this one, 4.5 divided by 3, multiply 2 and 2, it's going to be 3 over 2, actually. And for this one, 4.5 divided by 1.5 is going to be equal to 3. You can average them and you get this one. You can do the same for the low skew inverter. Now you care about the pull down network. So you get the same sizing of the unskewed gate, but the one in the pull up, you get it actually halved. So 2 becomes 1, the 2's here becomes 1 and 1, the 4 becomes 2 and 2. This is the low skew circuits for the inverter, the second 2 inputs NAND, the 2 inputs no. So what will happen, you will do the same. This is the up and down. So we sacrifice the one in the top, so it's 1.5 in the denominator, and here you have to have it as 3, up and down. We sacrifice the one in the top, up and down, and we sacrifice the one in the top. Get the input capacitance, it's 2. Get the input capacitance here, so it's 3. And get the input capacitance here, it's going to be 3. And from this, you can get the result. 2 over 1.5 is actually 4 over 3. 2 over 3 is the same. 3 over 1.2 is 2. 3 over 3 is 1. 3 over 1.5 is 2. And 3 over 3 is equal to 1. And you can get the average for each one. This is the way you calculate the logical effort for the skewed gate, where you favor the transition. And that's actually the main difference between the skewed gate, where you favor the edge or the transition, and the asymmetric gate, where you favor the input and not the edge. So basically, the skewed gate is more precise or more detailed than the asymmetric one. Now let's have some exercises. This is actually for we extending the inputs where for the NAND and the NOR to 3 inputs, and we want to get the logical effort for each gate on only its critical transition. So what we did is we actually draw the unskewed. This is the unskewed for the 3 input NAND. This is for the 3 input. No, the sizing is 3 and 3 and 3 in the pull down. We are compared to the inverter. The inverter is 2 to 1, and in the pull down you have 1. And now you have 3 transistors, so it's going to be 3, 3, and 3. The pull up is 2 and 2 and 2. For this one, the sizing is in the pull down, you have only a single transistor to the ground. So you have it the same sizing as the inverter, which is going to be 1. So you have 1, 1, 1, 1. In the pull up network, so you have 3. So it's 6, 6, and 6. If you have a single one, you will have 2. If you have 2, you will have 4 and 4. If you have 3, you will have 6 and 6, 6. If you have 4 transistors, you'll have 8, 8, 8, and 8. But for this one, it's 6, 6, 6. So what happens is, now we will do the high skew and the low skew version for each one of the NAND 3 input and the NOR 3 input. So the high skew, you keep this one, but you have the one below, the opposite in the low skew. So you have 1, 1, 1, and you have 3. For this one, you keep the up or the pull up network. You keep and you have the pull down network. You here you actually keep the pull down network, and you have the pull up network compared to the unskewed version. Now, to get the critical logical, he didn't say find me everything. Find me only one logical effort for each one of them. Now, so you don't have to double your work where you find both of them. Which one is the critical? The critical one here, since it's high skew, it's going to be the up. Here, it's going to be the up. Here, the critical one is going to be the down. And here is critical one is going to be the down. Now, since we are focusing on the critical transition, all of them, in all of them, you should divide by 3. Because they are all critical. The one that you divide by 1.5 is the one that is not critical or the one that you didn't fail. So now you just calculate for one of the inputs, 2 and 1.5, 2 and 1.5 is 3.5. For this one, 6.5, 6.5. For this one, you have 2 and 3, which is 5. And for this one is actually 6 and 1, which is 7/3. Now, this is what we get for the NAND. So the NAND, if it is high skew, is going to be, sorry, I'm calculating the wrong one. For this one, I was calculating this one. It's supposed to be this one. So 1 and 3 is 4, actually. 4/3. And here we have 3 and 1, which is 5. So here, this one is 3.5/3, which is going to be 7/6. This one is 4/3, which is this one. Now for the NOR, 3/16, which is 6.5/3. If you multiply 2 and 2, you get 13/6. And this one, it is actually, yes, 4. This is 4, actually. 3 and 1 is 4. 4/3. This is the way you calculate the high skew and low skew logical effort. Now, here are some observations in general. For speed, for the NAND and the NOR, some people will say the NAND is better than the NOR, but now we have the tools to help us on whatever the design is. You can get the design using NAND, you can get the design using NOR, apply the logical effort and see which one is better. Similarly, if you have many simple stage or fewer high end stage, and we give you a high fan end stage, and we give you some example for the multiplexer. Also the ordering, where the latest arriving input is making the commutative property matters. They are not equal anymore. For area and power, many simple stage versus for fewer high fan end stage also important. And I should tell you that we will talk about the power in a later chapter. I believe after a few videos. This is what we want to talk about today, and next time I'll see you for the next.